So M was, I have a chromosome that is 13 million base pairs long, so 13 million is M, okay? And I'm being asked for what is the probability of finding 1,201 errors out of those 13 million base pairs, okay? The problem said that you can expect to find one DNA error every 10,000 base pairs. So probability of error is 1 over 10,000 or 0.0001, okay? The other option, this is binomial, it's either there is an error or there's not an error, okay? So probability of no error is 1 minus p error. This is going to be equal to 0.9999. Okay. I want to know the probability of getting 1,201 errors, okay? So x is 1,201 errors. This is now my capital P, use my Gaussian distribution equation, okay, to solve for this. Before doing any math whatsoever, okay, what do I expect the probability of 1,201 to be? Probably. Probably pretty small, because where do what is the average number of errors I expect to find? What is that answer? It's mu, it's the mean, right? It's number of total base pairs times the probability of finding an error. So this is 13 times 10 to the 6th times 0.0001. This is 1,300 errors. So this is where my distribution is centered. This is the most likely thing for me to find. Most likely outcome, okay? Standard deviation is equal to the square root of 1,300 times 0.999. Okay, this was just MP times 1 minus P error, or P no error. This is equal to 36, okay? So I already expect to be within plus or minus 36, or maybe plus or minus 78 of 1,300. 1,201 is more than that away. I know the probabilities should be pretty small, okay? So if I plug everything in, I have 1 over the square root of 2 pi times 36. This is e raised to the, remember, minus 1,201, negative 1,201 minus 1,300. Okay, that's all squared over 2 times 36 squared. 0.0111 e to the negative 984 over 2592. 2.53 times 10 to the negative 4th. This is my probability. Or if you want to put it in a percent, 0.025, you could multiply by 100%. People like to report it either way. I don't usually care too much. This is the percent chance of finding 1,201 errors. Okay.